Thank you. Thanks for organizing this seminar series and thanks for inviting me. Today I'm going to talk about combinatorial methods for Minkowski tensors of polytopes. This is joint work with Niklas Lifshitz and Amy Wiebe. To give the general motivation, so the main object of this talk will be Minkowski tensors. So they are generalizations of intrinsic volumes, and they give geometric data about convex bodies. And so they are tensor-valued functions, and they are isometric covariant. So they actually behave nice under some distance-preserving transformations. And they are especially used for studying on morphology of structures. For example, in astrophysics, they are used for in the studies on morphology of galaxies. They are used in material science. They are used in studies on microscopic structures, so on the geometry of microscopic structures. They are very nice, but there is a problem that when the dimension and the parameters here increase, then it gets very hard to compute them. So we would like to have an easier way to compute them. And one of those ways is coming up with a generating function so that we can obtain tensor entries, at least for some classes of polytopes. For example, we especially focus on the case for polytopes. So for volume tensors, it's done by using moments on polytopes, and for surface tensors in our study, we provide an analogous formula. So this is general motivation, and during the talk, I will first give definitions and the background for Minkowski tensors, and then we will talk about the connection between moments and Minkowski tensors, and then I will continue with surface tensors. So I said that Minkowski tensors are generalizations of intrinsic volumes. Intrinsic volumes give scalar data about the geometry of a convex body. So for a convex body, intrinsic volumes are defined as coefficients of this polynomial on the right-hand side. So here, lambda is Lebesgue measure, BD is unit ball in RD, and kappa D minus J is volume of D minus J ball in RD minus J. So what we do here is we take epsilon balls and we take Minkowski sum of our convex body with the epsilon balls. Then this gives us a kind of parallel set. So this here is called a parallel set. And then we express, so on the left-hand side, we have the volume of this Minkowski sum, and on the right-hand side, it's a polynomial in epsilon, and the coefficients give us the intrinsic volumes. So, for example, here, when J equals 0, we will have volume of 2 ball. It will be P here. For J equals 1, we will have volume of 1 ball. It will be 2, and for J equals 2, it will be volume of 0 ball 1. So normally we also write this expression of volume on the other side, and then it gives us this intrinsic volumes. Yes, some facts about intrinsic volumes. It's so this equation is also known as Steiner formula, and Steiner showed that the right-hand side is a polynomial. And intrinsic volumes are also called as Minkowski functionals. That's where the name Minkowski tensors will come afterwards. And intrinsic volumes of a convex body do not depend on the ambient space. So this is one of the nice properties. And the name intrinsic was given by McMullen in 1975. And as I said, it gives scalar data on the geometry of convex body. For example, the dth intrinsic volume of a convex body, like d-dimensional convex body, it will give the volume. The zeroth intrinsic volume will correspond to Euler characteristic, etc. So this provides us a way to obtain some scalar data, but we would like to have more. So we also want to have some information about the directions and maybe about the position of the polytope, or a convex body. To also include those properties, local parallel sets were introduced. So they are defined as following. So we first choose a Borel set. It's as a subset of Rd times Sd minus 1, as is the sphere here. So we designate an area in our space. For example, here it's beta, and also we designate an area on the sphere. Here we chose omega, for example. And then the local parallel set is a set of points around this parallel area, such that we want that the points stay in this area beta. And we also want that when we consider normal, unit normals to those points, we want that those normal vectors to intersect with the area we chose on the sphere. So for example, here, those points on the side, they are still in beta, but when we consider their normal vectors and when we intersect them with the sphere, then they are not in the area we want, so we don't take those. So here only this yellow area gives us the parallel local parallel set for this A being beta times omega. And when we change A, of course, the set we consider changes. Yes, and from the volume of this local parallel set, we obtain a definition of something analogous to intrinsic volumes. So on the left-hand side, we have this volume of the local parallel set, and on the right-hand side, we have this polynomial. And the coefficients lambda j of this polynomial, they are called support measures. They are defined as coefficient of this polynomial. And for example, when we choose the whole space and the whole sphere, then the jth support measure coincides with the jth intrinsic volume. And we will use those support measures for defining Minkowski tensors. So we said that it's tensor valued generalization. So I would like to give the notation we use in this talk. So given a symmetric tensor, we can identify it by this array. So here I goes from 1 to d, and when it ranges, we get different entries. And EIs here are standard bases. And in this talk, so when we take this R's power or tensor power of a symmetric tensor, its components can be identified by those xij's, so that ij's range from 1 to d. So in the literature for Minkowski tensors, and also during this talk, when we say rank, we will mean this exponent of the tensor. So it's not the classical definition, classical rank we usually see. So for example, here if we have x in R3, then the rank 2 tensor x2 will be like tensor product of x with itself, and we can obtain it like that. So here we say rank 2 tensor because we like tensor x with itself and the exponent is 2. So this is one of the important points to keep in mind, the like what we mean by rank. So it's the exponent. Yes, now we can define Minkowski tensors. So for a d-dimensional convex body and for non-negative integers, Minkowski tensors are defined as follows. So for j from 0 to d minus 1, we have this formula. Here we already saw lambda j is the support measures. Lambda j is support measure, and here omega d minus j is surface area of unit ball in R d minus j. And when we have j equals d, and when s is 0, then we have this formula. And in this case, they are called as volume tensors. And when j equals d minus 1 and r equals 0, they are called surface tensors. But in this talk and in our work, we don't only call those tensors as surface tensors, but we say when j equals d minus 1 for other values of r and s, we still call them as surface tensors. So here, one of the things I want to mention is, so when we fix here j, it actually tells us, for example, in case of polytopes, it tells us which dimensional faces we want to consider. For example, here, when it's d, so it means we consider the whole polytope. When it's d minus 1, then we consider facets of the polytope. And this parameters r and s, it tells us the rank of the tensor we consider. So like when we change them, then it changes the tensors we put here. So here x to the r is like tensor product of x with itself r times, as I mentioned before. So we are especially interested in the case where we have polytopes. And let's see how those support measures look when we have a polytope. So what we want, I already mentioned. So we want that, for example, we want that this, when we consider a face of a polytope, for example, here, let's say we consider the facets, then we want that the volume to be only non-zero when we are in this area beta we chose, and we also want that when we consider their normals, we want the intersection of those normals and the area we chose to be non-zero. So here, this calligraphic H stands for Hausdorff measure. So, for example, if we fixed j here, let's say we fixed it as d minus 1. So we are considering the facets. Then here the Hausdorff, jth Hausdorff measure on the facet will give us the volume of the facet, and the d minus j minus 1 Hausdorff measure here, it's about this intersection with the sphere. So how it will be, for example, so for facets, the normal cone for the facet will be just a ray, and the intersection of this ray with the sphere will always be a point. So here, for example, when we put d minus 1 for j, this actually computes the 0th Hausdorff measure. So it will be non-zero when the intersection is actually just a point. And when we consider like other normal cones, and when we intersect them, if the intersection is not just a point, then it will vanish. And so this measure actually helps us to get what we actually want to have. Yes, then having this, like making it clear how this measure looks like, then we can express now our Minkowski tensors for a d-dimensional polytope as follows. So this part comes from the measure, and here we have the tensor values we want to add. And here it just becomes, it's just Lebesgue measure. So it's like computing the volume, but we also have the tensor entries. Yes. Let's see how this works over an example. Let's consider this polytope P. So when we have 2 here, it's, as I said, it's volume tensors. And when we change R, it will just change the rank of the tensor we are inserting here. So for example, for r equals 0, it will be the volume of the polytope, it will be A times B. When r equals 1, then we have like rank 1 tensor here, and we will obtain this. When r equals 2, we will have this tensor, and we integrate component-wise. So for each tensor entry, we integrate component-wise, and we obtain it like that. For example, in the applications, in astrophysics, apparently this, when we consider this, when r equals to 2, when we consider this tensor as a matrix, the trace of this matrix is especially used in some formulas, apparently. And we will see afterwards that for some values, they will give us center of mass, etc. So let's see what happens when r is 0, but s is non-zero, and when as j we have 1 here. So we have this expression with this measures, like from the support measures also. So how it looks like here, when j equals 1, as I said, we are considering the facets, and the intersection of the normals with the sphere will always be like 1 point. So from this Hausdorff measure, we will have the Dirac measure, Dirac measure, and the s, when s ranges, it changes the rank of the tensor we insert here, and the first Hausdorff measure over the facet, like it's one dimension, it will give us the volume. And here the indicator function, it just it just provides like the conditions we want, that like we want this facet we consider to be in the area we chose, and also we want the intersection of the normals with the sphere to be in the area we chose. So so in this case, we can actually express the Minkowski tensor like that here. So taking sum over all the facets, like the volume of the facet and the tensor of the normal vector here. And if we do the calculations, then, for example, when s equals 0, it will give half of the surface area. When s equals to 1, it will be like, so we were taking a sum over every facet. So now we also have this rank 1 tensor. So for each facet, we will have the volume of the facet times the outer normal vector, and we take sum over them. So in this case, for our polytope, it's 0. And indeed, when the polytope we consider has symmetrical faces, this will always be 0. And when we have s equals 2, it will be like entries will appear as rank 2 tensors, and we will have this result. Yes, this is how we calculate them, like as an application. And so this is nice, for example, for dimension 2, but when we increase the dimension and when we increase the parameters, it becomes, it gets hard to compute the entries. So I already mentioned that we want to find an easier way to compute the entries, and one of these ways is having a generating function. And for volume tensors, like we can obtain them by using the relation between the volume tensors and the moments on a polytope. Now I will give the definition of moments and how we use them. So for a d-dimensional polytope, let mu p then donate a uniform probability measure. Then for different indices, like different set of indices here, we will obtain moments as like this. So moments are defined like this. And here actually, in this probability measure, it will be the probability density function will be like scaling of, yeah, it will be scaled with, it will be scaling with the volume of the polytope when for a point in the polytope, and it will be 0 otherwise. So it's actually like scaling of the Lebesgue measure. Now we can give an expression like that. So maybe you recognize that this expression looks a lot like the definition of volume tensors we had just before, and we will come back to the relation. So we already showed how we see the tensors, how we see a rank R tensor, and we can also express a rank R tensor as sum of monomials with multinomial coefficients. So so here having the unit vectors, it will let us keep track on the like which entry it belongs to. And for example, we said that we have a symmetric matrix. For example, when we have the same value in like different entries, for different entries in the matrix, then it will change the coefficient of the monomial here. And we take, so we consider the partitions of R here also. Yes, then once we express our tensor like that, now we can rewrite the expression of Minkowski volume tensor by writing this, by writing our rank R tensor as we described here. So we can write it like that. And here, considering that these monomials, like this integral and using the Lebesgue measure, this part will actually be the moments. And we have those unit vectors, and we take sum over the partitions of R again. And we will have this volume of the polynomial, because we had seen that for moments it was the expression was scaled with the volume of the polynomial. Yeah, for example, for this polytope here, we compute the volume tensor. It's here, and then we can write it as volume of P times this expression, and here M10 and M01, they are actually like moments. If we consider this, yeah, here it's just to remind us how the formula was. So here the R was 1, so we were considering partitions of R, and we have 0, 1 and 1, 0. And here having the unit vectors tell us which entry it is, and it let us write it as a tensor. And this is actually, yeah, those moments correspond to center of mass in this case, for example. And in 2018, Kohns, Shapiro, and Struffels, they provided a generating function in the case of simplicial polytopes. So for the moments, for finding the moments, this is for finding the moments. So for finding the moments of the uniform probability distribution on a simplicial polytope, we have this formula, and yeah, here it's the sum is over triangulations. So we fix a triangulation, and for every element in the triangulation, we write this expression. And this generating function, it doesn't depend on the triangulation we choose. And when we write this generating function over a common denominator. So this is yeah, we just rearrange it and write it on over a common denominator, and then the numerator of this expression is called adjoint. It's called adjoint polynomial, and it's like this. So it's defined as a numerator of this generating function when it's written on a common denominator. So here again, it goes over the triangulations, and so for example, when we consider this square here, so we fix this triangulation consisting of sigma 1 and sigma 2, then we take sum over those, and we have these linear forms. So for example, when we consider sigma 1, we will write this linear form by using this x3 because it's not a vertex of sigma 1. And when we consider sigma 2, we will write this linear form for x1 because it's not a vertex of sigma 2. Also, I mean, so those ki's are entries of the vertices. And we mentioned that the generating function we chose doesn't depend on the triangulation we choose. So, as well as this adjoint polynomial. And they actually give a kind of, in the case of simplicial polytopes, they give a kind of characterization of polytopes. And when we, in order to say, obtain another way to write these linear forms, and also in order to see the vanishing set of this polynomial, we define a non-phase arrangements. So a non-phase arrangement of a polytope is given as follows. So we have a set of vertices. We take subsets of this set of vertices, and we consider those that so that they are actually not subset. How to say? Okay, let's make a small example. So in this polytope, for example, we consider set of vertices and their subsets. And then, for example, here for subset consisting of x1 and x3, this will be a non-phase because when we consider their convex whole, here this line segment, this is not a face of the square. As well as for the subset consisting of x2 and x4, because this line segment is not a face of the square. So each such subset gives a non-phase, and for each such subset we find this affine linear space, and we write for each vertex a linear form, and define this linear space, and the collection of those spaces, it's called non-phase non-phase arrangement of the polytope, and this collection is denoted with an f of p. One of the there are some points to notice here. So for example, when we fix, so for each non-phase we find, for example, for x1, x3, there is a triangulation of our polytopes such that this line segment is not a face of elements of this triangulation. So for any choice of different triangulation, there will be another non-phase, etc. And another point to remark, to note, is that those linear forms, they are written by considering the entries of the vertices, so they depend on the position of the polytope. Let's make an example. Again, we have the same square. So we said that x1, x3, and x2, x4, they give non-phases. And also any set of 3 vertices will give a non-phase. But in this case, when we consider this linear spaces, their intersection will be empty, so we don't need to consider those. And for example, for x2, x4, we write those linear expression for those vertices So for x2, it will be, so 2t1 and 3t2 equals 1. And for x4, it's here, the vertex. So it will be 4t1 plus 1t2 equals 1. So here they describe those lines. And their intersection is this linear space coming from this non-phase arrangement. And by using this expression of the adjoint, so we said that it was written by considering the triangulation. So we fix this triangulation. And for sigma 1, as I said, we write the linear form for x3. So it will be 4t1 and 3t2. And for sigma 2, we write the expression for x1. So it will be 2. So there will be 2t1 here and 1t2. So this gives us the adjoint. And then we consider those non-phase arrangements, those linear spaces coming from the intersection of linear forms for the non-phase. The adjoint actually vanishes on these points. For example, this adjoint polynomial, it vanishes on 1 over 5, comma 1 over 5, and it vanishes on 1, comma minus 1. So yes, Kohn, Shapiro, and Schoenfeld, they showed in 2018 that this adjoint polynomial has degree at most m minus d minus 1, and it vanishes on this collection of non-phase arrangements. In this paper, they also show that, so when we consider this non-phase arrangements in projective space, like when we consider the projective Zariski closure in the projective space, then for those there will be a unique polynomial that is called again adjoint that will vanish on the intersection of those linear spaces. So, and this polynomial in that case, it's important, algebraic geometrically, I would say, yeah, because it's used for defining the moduli space for some varieties. So I will not talk about those things, but if you would like to learn more about them, you can consider this paper. Yes. Now, yeah, we said that we can write the Minkowski tensors by using the generating function. And now we actually do it other way around, that we are writing the generating function in terms of the Minkowski tensor. So we take the Minkowski tensor, and then in the expression we substitute, instead of EI, we substitute TI, and we replace the tensor product with regular multiplication. And then, so this was the expression of the generating function for moments. And then we rearrange it, and we can express it like that. For example, here, so I already did this example, but in the example I did, we were just using the normal tensor expression. When we use the expression with monomials, with this multinomial coefficients, then we can express them like that. And to obtain this tensor polynomial, we just substitute here, instead of EI, we substitute TI, and we take normal multiplication. So that was all for the volume tensors. So for volume tensors, we have a way to write a generating function and to obtain entries of the tensors. And yeah, we wanted to see what happens when we consider actually surface tensors. So when we are in the case where J is D minus 1. So we had this definition of the Minkowski tensor with the support measures. So I already mentioned that the measure is arranged in a way that when we consider, for example, for a fixed J, when we consider faces of dimension different than J, then it will vanish. Or when we consider like normal cones that have different dimension, when we intersect them with the sphere, when the intersection has different dimension, then they will also vanish with this measure defined here. So what we get for as the expression of this Minkowski tensor for D minus 1 is actually like we are taking sum over all the facets, so that like we are taking this volume tensor for each facet. So here we have J equals D minus 1, but our facets have dimension D minus 1. So for our facets, this actually corresponds to the volume tensor of this facet. And then we have, depending on the S we choose here, we will have this tensor for the outer normals. And when we rewrite it in a way that, okay, we already had a generating function for volume tensors, so we are just writing it for each facet, and we take sum over them, and we obtain a generating function for the surface tensors. So when we rearrange it, before we were just using, we were using the expression of the generating function, and then we rewrite it by putting everything in common denominator, and also writing this generating function with the adjoint definition. So at the end we obtain this last line, so its own common denominator, and the numerator of this generating function, we again call it as surface adjoints of P. So we define something analogous to the adjoint of the polynomial. Now we define the surface adjoint of P. So it's this numerator. By the way, here we say that, so the generating function for volume tensors, it was for simplicial polytopes. Now here we are on the surface tensors, and we said that we can write the expression by taking sum over like facets of the polytope. So again, so the polytope itself doesn't need to be simplicial here. Here, as we only consider the facets, and we would like to write the expression for the facets, so we this generating function works for polytopes with simplicial facets. It's enough to have simplicial facets, because when facets are simplicial, then we are again falling back to the case when we consider volume tensors for those facets. Okay, each of them will be simplicial, and then it will fall back to the same case. Yes, so this is one of the important points. So yes, we define this adjoint, and how we compute them is, again, for each facet we compute the non-phase arrangements, and we compute the adjoints, like those we write the linear forms for each vertex and for facets, and we take sum over them. And we also noticed that for this with this definition of surface adjoints, we actually have again something analogous to the volume tensors case. So this surface adjoint is a polynomial, and it vanishes on the union of those non-phase arrangements for each facet. So we take the union over all the non-phase arrangements of the facets. So we have a generating function now, and we would like to extract coefficients from that. So one of the classical ways to do it is, okay, if we have a multivariate generating function, we can calculate the coefficient we want just by taking partial derivatives factored with those, and we evaluate it at 0. So we do the same. And okay, we said that our generating function works for polytopes with simplicial faces. But when our polytope is actually simplicial, then we have the adjoints. So then for each facet, we will have adjoint equal to 1. Because, okay, what we were doing to compute the adjoint, we consider triangulations, and we consider the vertex that's left, that's not on the triangulation. But if the facet itself is already a simplex, then we won't have anything on the other side. So we will only have, like, for each facet, the adjoints will be 1. And that makes the expression of the generating function much more simpler. So then all those factors will go away, and we will have this nice form. And for computing the derivative of this form, we provide a formula. We consider multiset partitions of this this set, and we write the expression as follows. So here, calligraphic LF means means that we multiplied linear forms defined by the vertices of this facet. How does that work? We can do an example. So for example, for this polytope, for each vertex, we write linear forms. So for x1, we have 1 minus t1. For x2, we have 1 minus t1 minus t2, etc. And the set of facets is, yes, all those line segments. And for r equals 1, our I will just be consisting of one element, where I is from the set 1, 2. So for example, for I equals 1, then we will take like derivative of the generating function for t1, and that gives us the first entry of our Minkowski tensor. So we just write the just apply the formula we gave. So we were saying here it was going over the partitions, but as I has only one element, so there will be only one partition. And yes, we said that this calligraphic LF is a product of the linear forms for each facet, linear forms coming from the vertices of the facet. And okay, we have this second power of this product of linear forms, but when we evaluate at 0, 0, they will just be equal to 1. So this factor will go away. And so, for example, for the facet that is convex hull of x1 and x2, what we do is, okay, we take the product of L1 and L2, and we take its derivative for T1, and we write this expression. And we do that for each facet and take sum over them. And then as a first entry, we obtain 25 here. And we do the same where I equals 2. So we take partial derivative for T2 with respect to T2. And again, we take the product of the linear forms, but this time we derivate for with respect to T2. So for example, for the facets consisting, that is convex hull of x1, x4, this derivative will be 0 because this linear forms L4 and L1, they don't have T2 inside. And we obtain the second entry as 10, and this result coincides with the computation we can do by considering the, like when we do the normal computation of the Minkowski tensor, it just fits with the result we have. Yes, and in our preprint, we also provide Sage code for computing, for extracting the entries, and also we describe algorithmically how to compute the adjoints. So that was what we have done so far, but there are still some further questions to continue on working on those. So one of them is like whether there are analogous ways to compute Minkowski tensors for other values of j. We did it for j equals d minus 1, but for example, what happens when j equals d minus 2? Yeah, it actually becomes a bit tricky because we used a lot the fact that the intersection of this normal cone with the sphere is just a point, but when we go to lower dimensional faces, the intersection will, for example, be an arc, or it will be something bigger, and we will also need to compute the volume of this intersection. So it will become a bit more complicated, but maybe there is a way to fix it and to make it work. Another question is, can we find such generating functions for some other families of polytopes? So for volume tensors, it was done for simplicial polytopes, and for surface tensors, we show it for polytopes with simplicial faces, but maybe it's also possible for some other families. And another question is, what are the properties of the vanishing loci of the surface adjoint polynomial we defined? So I mentioned that in the case of volume tensors, we said that this adjoint polynomial is actually important, and when we take this, when we consider those non-phase arrangements in the projective space, then it's actually a unique polynomial, and it gives a parameterization for some varieties, but is there also a kind of similar interpretation for the surface adjoint polynomial? So that we also don't know. Yeah, that's the questions we have, and here are some references, and thanks a lot.
Thank you very much, Büşra, for your very nice talk. Let's thank. Great. So any question, please unmute yourself and go ahead. Now I'm also, I'll stop recording.